Welcome to Learning Machines seminars at RISE, and especially welcome Magnus Röding from RISE, who's a research scientist here at the Department of Agriculture and Food. Magnus got his PhD from Chalmers in 2013, and he's also now an adjunct professor at the Department of Mathematics. Magnus works with mathematics and statistics and machine learning for material sciences and microscopy. For example, using computer vision for microscopy data and statistical modeling of realistic virtual material structures. So much of the interest here is about the structure and the properties of materials. And Magnus is working on applications within hygiene, drugs, packaging, chemical production, and more.
Thank you for the introduction. So the title of my talk today is Microstructures and Mass Transport in Porous Materials. And I will talk a little bit about how we integrate physics, statistics, and machine learning methods into this area. And the nice introduction here was already given by Olof, so I'll just skip this page and go straight to the point. Well, starting very generally, discovering new materials is something that's been basically crucial for every single technological breakthrough. Like, for example, computers, LEDs, solar cells, lithium-ion batteries, and a plethora of other things. Materials and their properties have been central in some capacity for all these breakthroughs and many more. Traditionally, when you've been looking for new materials and with the properties you want to have, you've been looking into experimental materials discovery, like testing things experimentally, a lot of trial and error, synthesizing something and producing it and seeing what kind of properties it has. This is very time consuming. It's very costly. Most likely you won't be able to test everything that you would like to test. So the results are most likely suboptimal and so on. But lately, I mean in the last decades or so, to start at another end, the complexity of the parameter space of possible parameters, materials that you can explore is basically a bottleneck for all this kind of materials discovery. It doesn't matter if you're looking for a new drug or if you're looking for a new a revolutionary design of an airplane wing or something. It's going to be difficult to search through all the possibilities. But we have very powerful computers today. We have more accurate models than ever. We can simulate more than ever. So real experiments are complemented or replaced by simulations to an increasing degree. Specifically, we are very interested in porous materials. So porous materials is basically some kind of material which has a pore space, or if you will, vacuum or air, or some parts of it where you don't have anything solid so that air can flow through or liquid can flow through or something like that. And this is like a very general type of material that you have in a broad spectrum of applications. For example, in Band-Aids and other hygiene and wound care products, you want to have transport of blood or something else away from a wound. In coatings on pharmaceutical pellets, you want to have just the right amount of release from a pellet or a pill to get the right effect of the drug. In different kinds of filter applications or separation, for example, a coffee filter, you want to let the right things through and you don't want to let the other stuff through. And you have lots of examples. I mean, in catalysis, in batteries, other hygiene products like diapers and napkins, paper, whether it's packaging or just a regular A4 paper, in all these and many more, porous materials are key in different ways. So what do we do with porous materials? Well, we tend to be very interested in how things are transported through these porous materials, like, for example, in a filtration application or controlled release for pharmaceutical industry. And what it often is for us is that it's sort of a chain of different things that we try to link together, and the chain looks different in different projects, but I've made an attempt to sort of link it all together. It usually starts with, you know, trying to understand some sort of material and what it looks like. And the obvious way to do that is to use some sort of imaging technique. It could be X-ray tomography, it could be electron microscopy, it could also be light microscopy, or something like this to characterize the structure of the material. And when it's a porous material, what we typically want to do is we want to identify which parts are porous, because the porous part and its geometry, that's what's going to determine the properties that we're looking for. So we do a lot of semantic segmentation of 2D and 3D image data, and sometimes 3D plus time as well, or 2D plus time. We do other measurements, which are not imaging techniques, but rather different other kinds of physical or chemical measurement techniques to understand what the structure of something is, or making a measurement of some dynamic property like a diffusion coefficient, for example, how efficiently particles are moving in a material. Once we have some idea of what a material looks like, it's also interesting to sort of, you know, quantifiably in some way characterize what it looks like. And that's where spatial statistics and geometry come into play, like estimating what is the surface of something, what is the volume of some features we have, or other ways of characterizing the volume. Like, for example, if we have a distribution of pore sizes, do we have a few large pores or a large number of small ones, and so on. So a lot of like quantitative characterization. And since I said in the beginning that, I mean, there's this tendency that more and more experiments are moved into the computers. You do virtual experiments instead. That means you will be interested in developing virtual material structures as a way of exploring different possible candidate materials in the computer, which is going to be a lot more cheap than doing the actual experiments. And then we have like stochastic geometry, for example, Gaussian random fields and other kinds of spatial statistics and models to model realistic materials. Another part of it is to, I mean, what properties do the materials actually have? In many situations, you can do experimental measurements of these typical like transport properties, like how fast is a fluid transported through a material, or how fast are particles diffusing through. But you can also simulate them. And we collaborate with people who develop these Lattice-Boltzmann method, which is sort of one way of computational fluid dynamics. The other even more standard way would be finite element methods. They have pros and cons. So we can simulate diffusion, and we can simulate fluid flow and other things, which I'm not going to talk about today. We are also interested in trying to predict the properties, not just to simulate them by conventional numerical methods, but trying to predict them from the geometry as a means of sort of understanding how the geometry and the properties relate. And to that, we use analytical models as well as machine learning models. And finally, which would be sort of the key step, the holy grail, would be what is often referred to as inverse design, or basically to solve the inverse problem of, given some prescribed properties, find a material which satisfies those prescribed properties. And in all of these steps, we have, you know, different statistical methods, we have machine learning methods, and so on. So I thought I would give a few examples basically today of what we do in this space, with a focus on the machine learning methods, of course. So the first example I would say something about is focused ion beam scanning electron microscopy, which is an imaging technique that we use a lot. The idea of FIBSEM, it's interesting because the data tends to look a little bit different than from other techniques. In this FIBSEM technique, you're basically peeling off a slice to get a flat surface, and then you're imaging the flat surface with a scanning electron microscope, or SEM, which is a surface imaging technique. It's not a volumetric one, it's a surface one, so you get 2D data. And then you slice another, peel off another slice, image again, peel off another slice, image again, and you get a sequence of 2D images, which gives you 3D volumetric information. But this is not the typical way you would do it if you do tomography, like at the doctors, or if you do like scientific tomography with X-rays, then you would get actually true 3D data. This is not true in the sense that it's more of a 2D sequential kind of data set. And that makes the image analysis a little bit special as well. Just to illustrate here what a data set might look like. This is one of the pharmaceutical coatings I talked about. This is from a collaboration with AstraZeneca and the electron microscopy researchers at Chalmers. So we started doing like basically what I would refer to as sort of a classical machine learning approach to it, where you do manual feature engineering. We looked at what kind of information do we need to classify one pixel, and we found out that we need to incorporate neighborhood information into it. So the way we did it in this first approach was to extract intensity information from 5 slices in each direction from the voxel of interest, and also in the XY plane. So we extract information from the plane, but for several different slices. So we get a 3D box, which is centered around the voxel of interest. And then we extract information at different scales by basically a Gaussian scale space, where we smooth the data with a Gaussian with different standard deviations, corresponding to different spatial scales, basically. And you see some examples of what the data might look like here. And then we take this data, which is for a bunch of different scales, for a bunch of different 2D slices, and we plug it all into a random forest classifier. So what we get is a pretty decent performance on the test data. We get like 92% accuracy, and the porosity, which is sort of the fundamental of all the geometric properties that we want to get right. We expected it to be 30 because we knew what the material was. We got something very close to it. So it was a very good first iteration, at least, to use random forests. But then sorry?
Question. So the classification here, what is it that you're classifying?
Oh, sorry, I didn't say that actually. What we do have is that we have manually annotated data for parts of this volume where we have manual annotations for what constitutes the pore parts and what is the solid parts where we actually have the material. So this is the pore space that you see here. This is a segmentation of the pore space in which we can have fluid transported. So it's a binary classification problem.
Okay.
Yep.
Thank you.
But then, as you may suspect, this is not likely going to be the state of the art for this type of problems. We looked into convolutional neural networks as well, and I'm not going to talk about that because I realize the audience knows all this stuff. But basically, what we did was what we used as an input for the CNN was roughly the same data that we used as input for the random forest, but we didn't pre-process it. So we took essentially the same 3D box and plugged it into a 2D multi-channel CNN, and we investigated different sizes of this box to find the optimal size. And eventually we used this sort of classical CNN structure with convolution layers, max pool layers, and finishing off with some fully connected layers to once again make the same classification into pore and solid, or pore and non-pore. We got better results from the CNN than we got from the random forest. And you see here some examples of the different sizes of these neighborhoods that we evaluated. And what we found actually, which is interesting, we used a sliding window approach where we trained the CNN to predict or classify a single voxel. And then in a sliding window approach, we just loop through the image line by line. I understand that this might seem a little bit odd considering that it's sort of general consensus that fully convolutional networks would be state of the art for classification tasks like this, but we actually tried that and we weren't really able to get so good results with that. And I think the explanation might actually be that since this is not sort of the standard data that you see in the literature, often you have 2D data with RGB channels, and here we have channels which do not correspond to RGB, they correspond to Z coordinates instead. So this being a relatively different situation, we don't really know what the state of the art is. But what we found for now is that this seems to be, this is the best of the approaches that we have investigated. So we see that we get a little bit of accuracy increase, a couple of % in the test data from the random forests to the CNN.
Another question. Okay.
Yes.
So the input to the model, how does that look? What is in the input?
So the input is basically this 3-dimensional box, or rather like 2D channels. Between 3 and 11 2D channels is what we investigated. The optimal one was for 3 channels. So that would be, if I go back here, so here is the voxel of interest, the one we want to classify. And this is the slice in which their voxel is. And we take that slice, we take the slice before it, and we take the slice after it. So we have dimensionality of 3 in the Z direction, 3 slices. So it's 3 2D channels. And then, yep.
Information is in these slices. Is there information about whether you have a pore or not, or is it something optical, or what is it?
So basically, I mean, roughly speaking, the solid parts are going to be somewhat brighter, and the pores are going to be somewhat darker. But I mean, it's not that easy, considering that you would have sort of a shine through effect, as they call it, that you see a little bit of the material that you have further into the structure. But very roughly speaking, the brighter parts are solid, the darker parts are pores. But that was also a reason, I mean, we needed to do manual annotation, because basic thresholding and filtering gives us nothing here. Very poor performance, just because the overlap of the intensities is considerable. But you can envision it as dark regions being pores and bright regions being material.
Thank you.
Yep. So I'm going to move to a totally, oh, sorry, I forgot this slide. I would just like to sort of think a few ideas that I have for how to improve the ML part here. The experiments are very expensive, and there are approaches for simulating realistic data from this FibSem technique. And then there have been some attempts to do that and to use that as training for fully convolutional CNN in their case. And that's sort of an interesting question for the future, whether we can use that to regularize our CNN and make better predictions on the real data. Another thing is that the annotation is very expensive. In this data set that I talked about, we only annotated about 0.5% of the entire data, and it still took a couple of days for the person, for the imaging expert to do that. So the question is if there are semi-supervised approaches where we could somehow utilize all the unsegmented data for the training of the CNN. And the third one was what I already mentioned, that we tried fully convolutional U-Net type CNNs. It feels like it should be better, but from what we have seen, it appears they are not. But I regard it as an open question, and with the right design, it's possible that it could be better. But it's an open question for now. So with that, I'm going to go to a totally different analysis technique and discuss AI-assisted data from that. Another technique that we use a lot is something called fluorescence recovery after photobleaching, or FRAP for short. The basic idea behind FRAP is that if you have fluorescent particles, which are shining when you illuminate them by a laser, uniformly distributed in a sample, what you see in the microscope is going to be a uniform intensity. If you bleach them, meaning that you kill the fluorescence in a spot, which is typically circular or rectangular, you kill off the fluorescence, and the profile that you're going to see is something which is not uniform any longer. You're going to see something which is uniform outside this rectangular spot we have in this example, but you're going to see a substantially decreased fluorescence in this region. And then the fluorescent particles is going to keep on diffusing and eventually smearing out this region more and more. And when you image this type of process, you get information about the diffusion coefficient, so the mobility or the speed at which the particles move. So basically, in physics terms, you could say that you perturb an equilibrium and then you observe as it moves back to equilibrium until you have a uniform intensity of particles again. So you can see some real data here. This is directly after this bleaching where we kill off fluorescence in a circle. And you see that this spot sort of degrades and disappears with time. And eventually we don't see anything anymore. So if you plot the mean intensity of the fluorescence in the region that you bleached, you're going to see something which eventually recovers because of this diffusion, and you're going to have the same intensity again. So this type of curve is the data that we have from which we want to try to estimate the diffusion coefficient and other parameters. So we have a numerical model for doing this, and I'm not going to talk about the numerical model, but basically it's a diffusion equation that we solve because it's a physical diffusion equation of sorts that we are observing. So we solve the corresponding numerical equation, and we do it on the same grid that the image is defined at the same resolution. We do that using some Fourier domain method, so it gets reasonably fast, but it is still rather slow. So if you would do the conventional thing, which would be least squares fitting, it might take a few minutes if you have a few data sets and so on. And we were interested in asking ourselves, can we accelerate this with AI methods? And the answer is yes, we can. So we have a few parameters that we need to predict. It's the diffusion coefficient or mobility. It's also an additional initial concentration, but we don't have to care about that. It's also something which we call the bleaching depth, which is basically how large a fraction of the fluorescence have you killed off with your powerful laser. So we generate synthetic data, curves like this. We vary the parameters, we vary the amount of noise, and we generate about 1 million of those and 250,000 for validation of test. And we plug it into a conventional fully connected neural network, like 4 layers, 128 nodes in each, nothing fancy. And we find out that we can actually train it to perform almost exactly the same as least squares does. We have real experimental data here that we evaluated on. And if you see here, the least squares fit with a conventional numerical method, and the curve, which is based on the predicted parameters from the ANN, and they are virtually indistinguishable. And if we do that with 20 replicates from, this is 20 real experiments, we get a slight difference in these confidence intervals for the 3 predicted parameters, but the difference is very small and not statistically significant. So we get something which is like orders of magnitude faster, with essentially the same performance as the least squares. I thought I would bring up in each section a little bit about sort of possible ML ideas for what you could do more. What I've been thinking about is whether we should have added noise as a data augmentation procedure, thereby having new noise in every single epoch of the training. I guess it's not obvious, given that we already have 1 million training samples, that this would improve anything, but it's an interesting question whether it would. Something more interesting is that we trained this in a proof of concept sort of setup where we had fixed the number of points of the curve that we generate, and the time values and everything is fixed. But in a real setting, you might have different experiments where you have different experimental settings each time. You can standardize a bit, but you will always have to change a little bit. So the question is, can we change, can we adapt an architecture like this to be able to adapt to different experimental conditions by teaching it to vary other parameters as well, not just the actual data, but the time coordinates, the X coordinates of where the data lies and so on. I see we have a question.
Hi, I'm Farouk. I also work at RISE.
Hi.
Interesting result. My question about the neural net that learns how to do this diffusion coefficient fit, how long does it take to train the neural net? Because I have also been working with surrogate models, and one common criticism with these problems is that if the initial training of the neural network takes a long time, that
Yep.
kind of defeats the purpose that it's fast.
Yeah, absolutely, and that's definitely a point. And I ran the training before I had access to really good GPUs, and then it took 10 days on a server grade CPU. But then we tried on, so that's what the paper mentions, something like 10 days. But when I tried it on T4 GPUs, which are not sort of very expensive, it took more like 1 day of training. But sure, it still takes some time, absolutely. And that was a point, and I think that's a point I've heard as well. I think in order to motivate approaches like this, you would have to make them at least more flexible, so you don't sort of fix them to a single experimental setting. So you have to redo the training, because then it's going to take even more time. So make them flexible, and also use them in cases where the numerical model is very slow. So there's, you know, some really good benefit at replacing it with an ANN model. But it's an interesting point. I mean, it's not always worth doing this. Yep. I'm going to move to another technique where we have something very similar. It's called small angle X-ray scattering, or SAX for short. It's actually a very similar setting to FRAP in terms of what the data is going to look like. But here we have samples that we irradiate with X-rays. They collide with the electrons in the material in the sample, and they scatter, meaning that they change direction. This is sort of a way of probing the distribution of the electron density, which is what you map with a technique like this. So basically what the measurement is, it is the intensity of the scattered X-rays as a function of a scattering angle. And a scattering angle corresponds to a wave vector in frequency space. So you basically get curves looking like the illustration here. You don't have to understand the technique. To be honest, I don't understand the technique much. I understand precisely what I have to need, what I need in order to do the modeling that we have done here. But in principle, you can fit the model to these SAX curves by least squares, like would be the conventional thing for FRAP. But in this case, it's very computationally heavy. And the question this time, and more motivated this time, was, can we speed it up with machine learning? And the answer, of course, is yes, we can. We can simulate synthetic data basically by generating realistic material structures, Fourier transforming this electron density model that we have, and extract simulated SAX data from that. So we use models looking like this, which are realistic models for many types of random media that you can encounter. So we have investigated two-phase media where you have a solid part and you have an air or vacuum part, and three-phase ones where you have a solid one and you have water on the surface and you have an air part. So we simulate the kinds of curves that I showed you before. These are some examples of what the simulated data can look like. And we want to train some sort of machine learning algorithm to predict the material parameters from curves like this. So we generate 500,000 in the training data and 250K in the validation of these curves. And we use XGBoost to predict the parameters. And the parameters here would be the volume fractions. So how much solid, how much air, and so on do we have in the structure. And also a length scale specifying how large or small the structures are. And we get reasonable accuracy. It's difficult to get really good accuracy because it's not just a matter of noise in the data. It's also a matter of the inverse problem that we are solving being not very well defined, because as a matter of fact, there are many different structures that correspond to the same SAX curve, and therefore there's a limit to the precision we can get. And this is precisely what we see here when the precision isn't better than it is here and the scatter plots don't look too well. It is because the inherent difficulty of estimating what the true structure looks like, because the SAX data is relatively difficult to work with. But we do get a speed of the prediction which is superior to if we would have used least squares, like many orders of magnitude. It's at the level where it's might not even be feasible, depending on your type of model, to actually do least squares. So just to say something about the ML ideas, I mean, it would be something similar to what I have in the FRAP case. We have the same thing here, that we have basically fixed what's on the x-axis of these curves. And the question is, can we adapt the architecture to deal with different combinations of experimental parameters, such as how many points do we have in our generated curve, where are those points along the x-axis, and so on. And that's, I would say, a very interesting question for lots of chemical analysis, type of chemical data and physical data. Can we train AI architectures to deal with that sort of stuff? It's not obvious how to do it in a good way. So for the final parts of this talk, I would change topics actually to go to sort of the other end of this this wheel that I showed you in the beginning, namely when we have information of different kinds about the material, and we want to start exploring the material and understanding its connection to its properties. And in our case, it's typically the mass transport properties, like I talked about before, fluid flow, diffusion of particles as they move randomly in a material, and so on. So to give just a couple of examples, porous materials, we use them for these mass transport properties. We have fluid transport in a band wave. We want to transport blood and other liquids away from a wound to keep it clean and nice. We want our coffee to go through the filter, but we don't want the actual coffee powder to go through the filter. So we want selective transport. We want to have controlled release of some active pharmaceutical ingredient, because we don't want to get the whole dose at once. That's most likely not going to be good for us. So we want to have different layers, filters, coatings, and so on, which control this transport the way we want it in different ways. Basically, I mean, a porous material mathematically, how do we represent it? Well, it's just, we think of a two-phase or binary structure in some domain, and we think that we have we consider an indicator function. We just say we have some function which is 1 where we have solid, and which is 0 where we have pore. So the transport of whatever we are transporting only occurs in the 0 part. So we can think of this as a compact set, like a cube, ideally with periodic boundary conditions, so we don't have to worry about what happens at the boundary. So it basically boils down to, we have a binary 3D array, and we can do the simulations in that. So that's basically what we deal with in terms of the data structure. It's just binary 3D arrays, cubic typically. So mass transport simulations, I'm not going to talk much about this, but we collaborate with people at Chalmers who are experts at the Lattice-Boltzmann method, which is an easily parallelizable method and very good for large structures. So we simulate 2 different kinds of properties. One is effective diffusivity, which basically says something about if we have obstacles in the structure, how much obstacles do we have, and what's the difference compared to having free diffusion in only a liquid. And we also compute the permeability, which is just a measure of how fast the fluid can flow through a structure. So these are the kinds of things that we simulate. But you don't have to bother about the details, because to be honest, I mean, I don't understand the Navier-Stokes equations for fluid flow either. I don't have to, luckily. To give you a couple of examples of concretely the kind of materials that we have analyzed, last year or a couple of years ago, we had a collaboration with Essity, where we studied a fiber structure that they intend to use in different hygiene products. We did some imaging of the structure using X-ray computed tomography. So we got 3D data of the structure. We did this basic image processing to extract the individual fibers. Once we have individual fibers, we can measure the radii. We can characterize what the curvature is, how much they bend or how straight they are. We can look into whether the material is anisotropic, meaning different in different directions, or whether it's isotropic, the same in all directions. And using this type of information, we could develop a virtual fiber model where the parameters are estimated from the real structure. And we could also validate by simulating the fluid flow and extracting the permeability, and also by measuring different geometrical properties, that this was something that was very close to the real material. And then we have a model that we can play around with and start varying parameters and see a little bit what happens when we vary the parameters. So we don't have to actually generate new real materials like this. We can just generate new simulated structures like this one. So sometimes it's referred to as a digital twin. I don't really use the term, well, except when I use the term, but basically something that imitates a physical system well enough to deserve that term. Another example is a coating layer that Tetra Pak uses on a cardboard that they have for their packagings. They produce a lot of packaging materials. This is to facilitate inkjet printing on the surface. And in order to characterize this and understand its properties, we use this FIB-SEM electron microscopy method I talked about before. And we used the random forest classifier method that I explained before. We developed a virtual model for the structure. And from this real structure and comparing it to the 3D simulation, we got very similar results in terms of this mass transport properties, the permeability and so on. So just a couple of concrete examples of what we do before I move to a little bit more imaginative studies, let's say. You will understand what I mean. Just a couple of examples that we actually do these things in a real industrial setting. So we actually help actual customers to understand what their materials are like. But we can do something which is more general, and this is more on the research project level. We can investigate generally what the relationships are between the structure of the materials and their properties. So basically, these properties, they depend only on the pore geometry. You don't have to think about like, is the fluid, is it water, or is it syrup, or is it air? It doesn't really matter for the sake of this. It depends, the properties depend only on the pore geometry, provided that you don't have a flow which is so fast so that you get turbulence effects and so on. But in our applications, turbulence is not a thing. So we can leave that to the people who design airplanes and so on. That means that we can basically look for relationships between the geometry of these binary 3D arrays and these mass transport properties that we can simulate and try to find relationships between them. And since we can generate so much data, basically unlimited, it's an interesting data science exercise how to make sense of such data. And if you want to explore the space of possible materials, it's actually a lot. Just to give an example, in pharmacology, it's estimated that the number of potentially active molecules is 10 to the 20 or even 10 to the 60 from theoretical calculations. In our case, if we have a cubic grid, which is n by n by n, the possible materials, so to speak, would be 2 to the n to the 3. And many of those binary arrays would be nonsensical because they would just be noise. So we're not interested in investigating them all, but it's still a very large number of possible structures that you can cram into such a cube. So basically the way of exploring that is to look into different types of realistic models that you can simulate, which is inspired from real materials. For example, here we have some fiber material, which is inspired from the hygiene materials that we have seen in collaboration with Essity. Just to take something else, here we have a structure which is inspired from coatings, pharmaceutical coatings that we have seen in collaborations with AstraZeneca and so on. So you can generate lots of different types of structures. You can simulate fluid flow through them or diffusion. And you can start to try to understand what the relationship actually is between the geometry and the properties. So doing this, we can do what in ML terms would be called feature engineering or feature extraction. We can compute different properties like porosity, which is the volume fraction of how many pores do we have, or how large is the pore space in which we have this transport. what is the surface of the interface between the actual material, the solid, and the pores? And do we have large pores? Do we have small pores? Do we have a distribution of the pores? How straight are the paths through the material? Are they very winded, or do they go pretty much straight through? There's a measure called tortuosity, which tries to summarize that. You don't have to care about the exact features here, but basically we can extract manually geometrical features, which makes a lot of physical sense, and we can try to build prediction models from those. So we can do that basically with, let's call it, white box relationships. There are many physically founded relationships in the literature, typically of power law type, like for example, the porosity to the power of something, the interfacial surface to the power of something, and so on. And you can make pretty decent predictions of, in this case, permeability from this type of relationships. But you're always going to be bound by the functional form here, because it's a relatively simple functional form. So you can move to, well, let's call it black box relationships, some sort of machine learning, where the bottleneck is no longer likely to be the functional form. The bottleneck is going to be the information content, in some sense, of these features or descriptors that you plug into the model. So if we investigate the exact same relationship by a conventional ANN, we just assume that the permeability is some more generic nonlinear function of these three features. We get an error which is substantially smaller. We also get a few more outliers, actually, which sort of illustrates that perhaps it's a slightly less robust than the physical model. On the other hand, you get on average better predictions. So it's always a trade-off. And one obvious question to ask, perhaps, since this is basically 3D images, it's binary 3D images that we have as our input data, and we can do feature engineering, or we can plug the entire 3D array into a CNN and see what happens. And it turns out this actually works pretty nicely. We have to reduce the resolution of these structures a bit, because the resolution that we need for the numerical simulations of the flow is larger than what we can practically plug into a CNN. But if we reduce it by a factor of 2, we can use a sort of pretty straightforward CNN architecture, and we can get a prediction which is actually noticeably better than the one that we get from the ANNs. Still a little bit of outliers, but on average, noticeably better. There's also one interesting thing that we can do, which I think is sort of a nice feature in terms of data augmentation. Since we have these periodic structures, and we know that if we shift the structure a little bit, I mean, it's still periodic and it still has the same properties. So we can do a very neat data augmentation in this sense, because we can randomly shift this periodic structure, we can mirror it, we can rotate, swap axes, and so on, and we're not changing its properties. So unusually good potential for data augmentation in this case. So some interesting ML ideas that I've been asking myself is that, can we combine a CNN where you use this full 3D binary array structure as input with an ANN, which use sort of manual feature engineering? Would it be any better? Likely slightly better. I don't know how much better. Something which I've been thinking about, I don't know if it's important, but you could think about, if, since these structures are periodic, I mean, usually when you do these convolutions, you're just keeping the valid part of the convolution. So the convolution is effectively decreasing the data set size a little bit as you go through the layers. Given that you have a periodic data, you actually don't need to do that. So you could keep the full size after convolution and maybe get a little bit more information. I don't know, it's probably not important, but it's sort of an interesting thought, as far as I think, at least. One other thing I've been thinking about in terms of CNN, I mean, in these cases, we know that if a particular CNN filter in the X direction is useful, it should be useful also to have the exact same convolutional filter in the y direction, because we know that there's a symmetry with respect to the axis here, because it doesn't really matter if we rotate the structure. So an interesting question is whether it would be practically meaningful to constrain a CNN in its training to work with these sort of symmetrized sets of filters in each layer. It might make some physical sense, but from an actual ML performance standpoint, I would be surprised if it actually gives something. I would expect that it doesn't, but it would be an interesting thing to try. And I realize I'm almost out of time here, Olof, but I thought I would just finish off with a little thing here on the end. The question is, why do we do this? Why do we try to establish these relationships between the geometry of a material and its performance or its properties? The ultimate goal of that, as I hinted in the beginning, is what is in this sort of branch or niche is called inverse design, namely for given that we have a property that we want, how do we find a material which has this particular property? So basically, we start with some prescribed properties and ask ourselves, can we find something which has those properties? One interesting case is to look at anisotropic materials and look at their properties in 3 different directions, because anisotropic materials are materials, like I said before, which do have different properties in different directions as opposed to isotropic materials. If we use an anisotropic Gaussian random field model, we can create materials looking like this, where you have, here's an isotropic one, it's the same in all directions. Here's a slightly anisotropic one, it's a little bit more elongated in this direction. And here's a strongly anisotropic one, which is a lot more elongated in this direction. So we can play around with length scales along all the 3 axes, and we can also control what the porosity is, so how much pore space we have over the whole structure. And in this class of materials, we have made an attempt at this sort of inverse design concept to find a material which satisfies the properties we are looking for. So we ask ourselves, given that we have these generation parameters, which are these length scales and the porosity, which parameters will give us a set of these diffusivities, which is, I mean, how fast does particles diffuse in this pore structure? And we have that information in 3 directions. So this is a difficult inverse problem, and it doesn't have a unique solution, because these structures that we simulate, these virtual materials we simulate, they are stochastic by nature. So we do a Bayesian formulation where we treat the prescribed property, which is this vector, as data. And we have a Bayesian formulation where we look for actually a prior distribution, a posterior distribution of these generation parameters given the data. And this works because mathematically, in this sort of Bayesian formulation with priors and posteriors, this property that we're looking for is actually mathematically analogous to plugging a set of observations or actual data into the Bayesian inference framework and looking for a distribution of the parameters of a model. So it's actually mathematically the same thing. We don't need to have data. We can have something, just a value that we're looking for. And we use something which is called approximate Bayesian computation, which is basically, I'm not going to talk so much about that, but basically we can sample values from this vector of the generation parameters. We can generate virtual microstructures from that model. We can predict the diffusivity in all 3 directions using a CNN that we have trained specifically for this task, which is something which is way, way, way faster than doing the actual numerical simulation, like many orders of magnitude faster. And we accept this structure as a part, or this parameter as a part of the posterior, if the difference between the prescribed property eta and the predicted property of the simulated structure eta hat is not too large. So basically we simulate lots of structures, and by doing that, by rejecting most of them and accepting a small number of them, we get some information about what the distribution of these parameters should be to get the properties we want to have. And just to very briefly hint here, the result of this running this computation is a distribution over all these different parameters of what the best values to choose are to get properties which are as close to the prescribed property as possible. This is once again very much a proof of concept, and this is very much an open question how to do this sort of thing in a good way. But this is sort of our answer in this setting for how to do this so-called inverse design and finding a structure, which is the optimal one. So hopefully, I hope that I have sort of managed to some extent tie together different parts here and sort of the fact that it all comes together here. I mean, we work with people who are experts at imaging techniques and other kinds of measurements. We have different kinds of data to analyze. I mean, in the case of images, it's typically semantic segmentation, or it's always semantic segmentation, but it can be other types of chemical, physical data that we analyze in different ways, some sort of time-dependent signal or something else, like I showed you in a couple of examples. I haven't talked so much about that, but we characterize materials using different geometric descriptors. We use the information that we get from the real world to design realistic virtual material structures, which we can play around with. We can simulate the properties. We can train machine learning architectures to predict the properties. We can use these as a way of circumventing the very computationally heavy simulation and instead use the prediction, even though it's approximate, in this sort of inverse design setting where we are trying to find materials which have the optimal properties. And although we are rarely sort of at the top of the game, so to speak, I mean, we could definitely do much more in all these areas, but we are getting reasonably good at least parts of this, and the aim is long-term to connect all these things and be able to sort of arrive at some sort of design process for new materials and helping industry with doing that. And with that, I'm pretty much done. So thank you very much for listening.
Thank you, Magnus. So do we have questions for Magnus? Perhaps I can start. I really like this. You really tied it all together and sort of you went the whole circle here. What would be the sort of what are the next steps? What are you going to do next year?
I would say one next step would be to sort of generalize this this sort of inverse design thing. How do we design different materials and do that for different types of structures? We did that for a simple choice because those structures I showed you here are very quick to generate, and that made this sort of proof of concept study simple. But there are other cases when the generation of structures like this is very computationally heavy, and then it would take some more time to actually do something like this. But in the long term, we want to do it for different types of geometries. Also, I've been thinking about, I mean, because there are people, perhaps not in this specific type of application field, but in other parts of material science, which have started to use like generative models, like what do you call them, GANs, for example, to simulate, like generate realistic looking material structures based on using such an architecture, which can be a very fast and neat way to explore the space of possible materials. Because, I mean, then you don't have these sort of computationally heavy ways of generating material structures. You can use a GAN, which is hopefully a lot faster. So you can accelerate the exploration of the space, let's say. And that's something which I've been thinking about doing. I'm not sure exactly what can be done, but it would be interesting to dig into the generative architectures to see what they can do for us here. And also, sorry, yeah.
You could probably include material properties in such a model as well.
Oh, you mean to teach it to generate something with a desired property, for example?
For example, yeah.
Yeah. That's actually something I'm not sure I've understood exactly what they have done, but if I understand correctly, some people in Zurich have done that for mechanical properties of materials. They have taught a network to generate something realistic looking that has a prescribed mechanical property. So it could possibly be done in this case as well. Yep.
Cool. So question from Farouk.
Hi, thanks for a great talk. I have a couple of questions. One, it seems that most of the stuff that you were talking about, you were comparing the existing physical or empirical models with machine learning models.
Yes.
And there seems to be kind of what people call a gray box, which is somewhat in the middle, where people use some physical constraints and on top of using a neural network.
Mm-hmm.
So have you considered such an approach? So that's my first question. And second question is generalization. So when people are applying black box models to physics applications, oftentimes a criticism is if we have a physical model and it doesn't work, then we can often tell, okay, there's a physical reason why our model doesn't work. Whereas with the black box model, we don't know if it's failing, or even if it's working, we don't know if it's learning the right physics. So what do you think, that can be done about this, and what you've done in your work?
Yeah, well, in the last study I talked about here, when we tried to find materials with some properties we were looking for, the final step, which I don't say here, is that once we have identified something which is like the best candidate, we actually validate its properties by running through the real numerical simulation and check what is the deviation between the predictions and the actual simulation. And I think this is really a critical step, because you cannot just trust the prediction model, because I mean, it might be very, very good at precisely the point in parameter space where you are, but it could also be terrible at precisely that parameter space. I mean, you don't know that. So I think validation using the conventional computationally heavy methods is a good thing. And when it comes, if we move up here to the example I had about, let's see, many slides. So here, when we have this Freck technique for measuring diffusion, what you can do there is, I mean, you still have your least squares model, and you can still actually do a comparison by starting by making the prediction of the neural network and using that prediction as a starting point for your conventional least squares optimization, and just validate that they are one and the same. Or roughly one and the same. That's going to go much faster, because you can skip most of the iterations of the least squares, because you're already at a very close to optimal point. So that's one way of sort of validating, in this case, that you have something which is good. But generally speaking, I think your point is very interesting. And this is something which I've been trying to say to physicists. And my feeling is that they don't quite always understand what you said. Namely that if you have a physically plausible model, you can extrapolate it, because sort of almost by definition, because it should be physically plausible in a larger region of parameter space. But of course, with a machine learning model, you cannot know that it is. So you have to be very careful about whether you're doing interpolation or extrapolation. I'm not really sure if there's a way of taking that into account in a good way. One thing that I've been thinking about, if we go to the, now I'm going to jump down again here. If we look at the, let's see. Sorry. If we look at the ANN models, for which we use like manually extracted features as an input, we know that some of the properties of the ANNs will not be the same as for the physical models. For example, if we go to the physical model, we know that if the porosity increases, the fluid permeability will increase, which is very physical. But we cannot say for sure that the ANN does that. I know I found some papers in the 90s that addressed the question of enforcing a neural network to be monotonic in its response with respect to the inputs. And that's something which I find sort of physically interesting. Can you teach an ANN or train an ANN to, I mean, not adhere to a strict like analytical formula like this, but to at least sort of maintain the monotonicity that if you increase the value of one descriptor, make sure that the output increases as well. I mean, that could be one way of sort of regularizing machine learning models and make sure they make slightly more, better predictions. But of course, if you move outside the training set, pretty much anything can happen. So monotonicity could be one way of ensuring that it doesn't go completely haywire if you go slightly outside. But of course, I mean, I wouldn't really see how you could ensure that it gives good performance outside. So maybe the best thing, the best thing you can do is to make sure they don't go completely nuts by enforcing monotonicity. That's sort of one idea I have. Otherwise, I'm not really sure what to do.
Thank you. Yeah, indeed, there's been work on imposing what people call soft constraints, so having these constraints in the loss term, and also some work on hard constraints where you can either design the architecture or introduce an optimization layer inside the network to enforce such constraints. So yeah. Thanks.
I can say one more thing, which is interesting. The fluid permeability is a positive number, and we made sure that the prediction is always positive by training it on the log of the actual permeabilities. These diffusivities that I talked about, they are values between 0 and 1. And before training, we actually applied a what's it called, a logit transform, turning it into a value between -infinity and infinity, training the network to predict that, and then doing the inverse transform, ensuring that the values are always between 0 and 1. I mean, this is, of course, a very mild regularization, but these are steps you can do to make sure that the values are not completely unphysical that you get out.
All right. We had another question from Sepide, who wrote it in the chat and then had to leave the meeting.
Okay.
If you have control on the new material that you are creating, I'm not sure whether the question is entirely formal.
Yeah, I mean, I guess this is maybe a question of sort of how we generate the material. In this case, we use parametric models for generating them. And of course, if you had a generative neural network architecture, you would be less in control, and they would generate things which only looks like the model you have, so to speak. But I mean, in this case, we are only using materials which are from well-defined parametric models. Therefore, we are pretty much in control of what's going to happen. They are still stochastic models, but they belong to a well-defined parametric class. Well, we can only guess if this was an answer to the question or not, but
perhaps someone else was wondering as well.
Yeah.
So with that, I think we should conclude this. Thank you for the talk.
Thank you. Thank you.
Next week, we meet again, and then Lovisa Hagström, who is a PhD candidate at the Department of Computer Science at Chalmers, will talk about the issue with understanding language from text alone. So that is March 24th. So thank you for today.
Mm-hmm.
Bye-bye.
Thank you. Bye-bye.